In this video, I'll describe how to make your C++ applications harder to hack. The first type of vulnerability I'll highlight is buffer overflow. Buffer overflow attacks take advantage of the lack of boundary checking on array access in some programs. This lack of bounds checking permits attackers to overwrite memory and redirect execution. To prevent this, use functions that perform bounds checking in substitution for those that do not. Format string attacks are possible when C++ programmers forget to add the string format specifier %s for a string input function. Users will be able to enter their own specifiers, and in tandem with the %n specifier, will enable them to overwrite data at any memory location. Dangling pointer attacks take advantage of pointers that are pointing at freed memory. Heap feng shui, also known as heap grooming, is a technique used to direct dangling pointers to attacker-controlled chunks of memory. STD system allows C++ programmers to access the command console. If STD system is used in conjunction with user input, another potential vulnerability is created. Attackers can take over a user's system with this function, so it should be avoided as much as possible. Time of check to time of use attacks take advantage of the time discrepancy between file access permission checks and the opening of a file. This time window allows attackers to overwrite file names and gain access to sensitive information. It would be safer to open the file first, then check permissions using the file descriptor with the fstat function. In your IDE, enable address space layout randomization. This places functions and data at random addresses to make it harder for attackers to exploit. Enable data execution prevention. This prevents data from being executed as functions. When you perform an integer arithmetic operation and the result surpasses the capacity for the assigned value to store, the outcome is an integer overflow. Integer overflows can be leveraged to perform buffer overflows. Use assertions to check for minimum and maximum values being breached. For unsigned integers, check if increments lead to values that are lower than the previous value, and for decrements, check for values that are higher than the previous value. You cannot use these checks for signed integers because signed integer overflow leads to undefined behavior. The Boost library offers defined behavior for signed overflows. You can use the std numeric limits to check for max signed values.